Hello, hey, good morning, or good afternoon, or good evening, wherever you might be, and whatever time it is. So in this tutorial, I'm going to do the fast Fourier transform using ofxMaxim, and we're going to be using a few new objects. That's the ofxMaxim FFT object, and we're also going to look into something called Octane analysis and break the frequencies we get from our FFT into average bands. And I'll explain a little bit more about that when we get to it. I'm not going to go fully into how FFT works. If you want to learn that, then probably better to find a better source. But I can give you a rough overview of what's going on. Now, there's two ways to look at music. One is in the time domain, and the other is in the frequency domain. The time domain is what you're dealing with when you've got a WAV file. It's a regular sampling of a sound in time. So you end up with a sequence of samples in a row at regularly spaced intervals. This is a useful view, but it tells you nothing about the frequency content of sound. You can get some rough ideas by looking at it, but basically it's telling you where the sound level was at a given point in time. And FFT is somewhat similar to additive synthesis, and what I mean by that is that all sounds can be seen as a collection of sine waves added together. With additive synthesis, you can theoretically replicate any complex waveform by taking precise measurements of all the frequencies in that waveform and put together the appropriate collection of sine waves at the appropriate amplitudes with the appropriate envelopes. In theory, you should have the same sound. Now, rather than synthesizing a complex waveform from scratch, FFT is a process that takes the existing complex waveform and breaks it down into many different frequency components. You can then manipulate those frequency components separately in amplitude, speed, etc. before they get put back together and they become a complex waveform again. So a plain English metaphor might be the fast Fourier transform would, if given a smoothie, it would find the recipe. How? You'd run the smoothie through filters and you'd extract each ingredient. And then why? Because recipes are easier to analyze, compare, modify than the smoothie itself. How do we get the smoothie back? We blend the ingredients. So to give you a visual demonstration, I've got a GIF that's useful. Am I in downloads? Yep. Okay, so if I go QL manage. Okay, cool. So this is our complex waveform. And don't worry too much about the math notation, because I'm not going to be going into that. But here you can see it broken down into lots of different sine waves. And then we take a measurement of all those sine waves, and then that maps to each frequency band. Cool. So there we go, and on with the show. Okay, so what we're going to do, we're going to use the objects that do all the gnarly stuff for us, and we're just going to make a little visualizer that will take an input and it will analyze it and give us something that's similar to a graphical EQ. So the first thing we need to do is get our header file in. And And then we need to add our audio out callback method. Takes our buffer. And it takes our int buffer size and number of channels. And what I'm going to do is I'm also going to do some basic sequencing to essentially automate the triggering of our sound. Or maybe I'll leave that for another lecture or tutorial. No, I'll throw it in. So we're going to have to build a timer as well to trigger our sound, and obviously there are OFX add-ons that can do this for you, but it's a fairly straightforward procedure, so we'll just use what's given to us with the openFrameworks library to do that for us. And obviously there's better ways to sequence what we're going to do, but you know, this way is fine for our purposes. So we need values for buffer size, sample rate, and now for our timer we need a start time, an end time, which is the length of the timer, and we need our current time, which is where we're currently at in the timer. We need a double value for frequency, and current sample. We need a double array for our outputs. And now we need all of our ofxMaxim objects. So, as usual, we need a maxi oscillator OSC. We need an envelope. We need a mixer. And here are the FFT objects. So it's maxi FFT, and it's our Octane Analyzer. Okay, cool. So, talk briefly about the fast Fourier transform. But what does the Octane Analyzer do? Well, when we've got our sort of whole frequency range, we can divide the whole range of frequencies into sets. We call these bands, and each band covers a specific range of frequencies. Now, it'd be better to do logarithmic averages. So, a natural way to do this we could split each average to span an octave. So, it's going to, each time we go up an octave, we're going to double the size of the average band. So our first octave would be 0 to 11. And then the second one would be 11 to 22 Hertz, and then the third would double, and that would become 22 to 43 Hertz. So that's jumped by 22 this time. The next one would be 43 to 86 Hertz. So that's doubled and become a band of 43 Hertz wide. And the next one would be 86 to 172 Hertz. So that's now doubled again, and it keeps on going up like that in a sort of logarithmic fashion. And it just makes for a better Analyzer. But anyway, continuing on. So we've done that. We need to now do our setup. So we need to set our envelope first. So env.set AD attack. So that's to 2000. env.set decay. Remember, these are arbitrary values, although decay always has to be greater than 1. ADSR. $4,000. Cool. Okay, I'm going to set our frame rate to 60, or at least try and make it so it's consistently 60 frames per second. I think this may be defaults anyway, but just explicitly type it. Sample rate is, as usual, 44,100 Hertz. Buffer size is 512. And set our background to black. Okay, if we do of setup screen, and that will just reset all the OpenGL screen coordinates and values back to the OF defaults. Okay, so we need to set up our FFT object, and that's simple as doing FFT setup. It takes 3 arguments: FFT size, window size, and hop size. And if you want to find out more about that, either look at the library and work it out for yourself, or Google it, sort of outside the scope. I'm just going to use the examples given to me from the examples that Mick, the guy who made the whole library, the whole Maxim library, he's got a bunch of examples on his GitHub, and I urge you to use those and play around with those, because they're all great. But I'm just going to use 10, 24, 512, and 256. Now we need to set up our Octane Analyzer. This takes 3 arguments, and again for what I said before about the FFT setup, if you want to find out more about it, then just have a look. But so you know, the arguments are sampling rates, number of bands in the FFT, and the number of averages per octave. So 44,100, 1024, and 10. Now the last number is what we're really interested in here, because the greater number of averages per octave is inversely proportional to how many octaves we'll have to visualize, basically, because that's what we're going to do. We're going to take all the octaves, or we're going to take all the bands that the Octane Analyzer will give us, and we're going to use them to manipulate circles on our screen. And it's a super basic example, but should hopefully get you thinking about what you might be able to do with this. There's lots of applications other than just a graphical EQ. Yeah, we're going to, if you want more, say, circles to play with, then I would decrease this last value here. It's inversely proportional, just remember that. So we need to set up the DAC. So that's 2 inputs this time, no, sorry, 2 outputs still, sorry, 0 inputs, a pointer to the base app, and sample rate, the buffer size, and then number of buffers. Cool. So let's make our timer, and this is going to trigger our note at the frequency we've made. So we can do that. What should we do? Right. So we'll do current. Oh, in fact, we need to initialize our timer. Otherwise, it's not going to work very well. So we need to set our start time. We set our start time to the amount of milliseconds elapsed since we started our program. So of get equals of get elapsed time millis, and end time, we'll just make that 1000 seconds, no, milliseconds, so that's 1 second. So here we can do current time equals of get elapsed time millis minus start time. So remember, this is during setup. So just to explain it, if you're not familiar with timers, we're going to set this to a sort of constant value, and then, well, it's not quite constant because it will change, but during the update loop, this number will continuously be getting bigger and bigger, and we will subtract this constant value, and essentially this will grow from 0 eventually to 1000, and at that point we want to write a conditional that will trigger and then reset our start time to the current elapsed time, so it's a sort of infinite timer loop sort of thing. So we can do that quite simply, as I said, by a conditional. So we do if current time is greater or equal to end time, then do something, else don't do something. Now, what do we want to do here? Well, first of all, we need to make sure that we're triggering the sound. So we haven't wrote the sound yet, but we know we're going to be using this envelope, and we know that the envelope has a member field called trigger, and that value needs to be 1 if we want to trigger the envelope, or 0 if we don't. So if it's time, if the time is right, then it's time to trigger our envelope. So we simply do env.trigger equals 1, else env.trigger equals 0. Okay, so that's cool. We also need to set our start time to equal the current time. And that looks fine to me. Okay. So we'll come back to draw. We'll define our audio out method now. So void of app audio out, float buffer as an input. And we need to loop through the buffer. and guess our current sample value. So current sample equals our envelope dot ADSR, and then we're feeding in our oscillator, so that's the input for the ADSR to return our output, which will be a double. So double input oscillator dot sine wave at a frequency, and then env dot trigger is the trigger for that. Cool. Here's the new bit. Basically, if FFT can process our current sample, then we want it to calculate the band magnitudes. So the Octane Analyzer, we need it to calculate its averages. So we can do this all in an if statement. So what we do is we do if FFT.process current sample, and what that's doing is feeding in this double value, and basically if it's returning a non-zero amount, i.e. it's truthy and it's true in C++, then do this. If it can't process it, then don't try and run the other code. That's all it's doing. So and it's simple as that. So now when we access the member fields inside the Octane Analyzer, they'll be full of values. Hopefully, I presume they will. Unfortunately, my computer's not fast enough to record video and give me error statements at the same time, so we'll have to find out if it does work. But anyway, so now we need to actually send our output something. So mix dot stereo, and then that's our current sample. It's the input, our array of doubles for the outputs, and mix it cleanly between left and right channel, equally between left and right channel, I should say. So, and then route our value to the correct index. Okay, cool. So that's sorting out all our sound stuff. Now all we need to do is we need to draw it. And this is pretty straightforward. So there's obviously just a whole range of ways you might want to draw it. And you don't even need to use this Octane Analyzer to draw it. You could quite literally draw all the frequencies at once. But just to keep it simple and very manageable, I think we'll just use the Octane Analyzer and kill two birds with one stone. So set the background. To black, and then I'm going to draw them in a straight line. So int I equals 0. I is less than oct dot number of averages. So I'm going to loop through all the averages basically. I can spell it right. And then I plus plus. And we're going to make our color map. We're going to loop across the whole color range in HSB. You might be used to HSL, which is hue, saturation, and luminance. I'm going to use hue, saturation, and brightness, but they're completely the same thing. And we're going to map the hue to where we're at with the number of averages. So super simple. In openFrameworks you can just do this. So we'll make our current color of color. I'm afraid I'm English, so I'm going to spell it properly. Color dot set HSB. So set the color from a HSB value. This takes 3 arguments. So hue would set the saturation to 255 and the brightness to 255. Now all we need to do is set the hue. So typecast as an int first, then of map needs to set the I is what we're mapping, and we're mapping that between 0 and the amount of averages. So oct number of averages. And we're mapping that between 0 and 255. Simple as. Okay, cool. And then we just need to set whatever we draw next to that colour. Okay. So really what we're going to do is just draw a circle. So we do of draw circle at some sort of value x, and we know that it's going to be a straight line that's consistent on the y-axis, so that's going to be in the middle of get height over 2, and it's at some sort of size, but we don't know what those are yet. But let's define them. So float size equals 1. So we're going to set it to a base, an absolute minimum size of 1. It's always going to be 1 plus extra size if there is frequency in this average that we're in the current average we're at. So plus, and we get our average value by doing oct averages I, and that's there is an array of averages values, which are all doubles, I think, in the Octane Analyzer, and just because it gets really big, I'm going to divide that by 10. And then we need to set our x position, and really I want this to be half of the screen long, and then we need that to be centered. So let's make it half the screen long first. So that's going to be, so int x equals of get width over 2 times I over oct number of averages. Cool. So what are we doing here? Basically we're working out a ratio of where we are in the index, in the amount of averages, and then we're just timesing that by the length we want it to be. So we're going to need to typecast this all as an int, so we don't get any problems. And then we need to shift it all so it's centered. Now this is half the screen long, so if I want this to be centered, I need to kick this up by a quarter of the screen. So I'll get width over 4. Cool. That looks fairly straightforward to me. All I think now we could do is modulate the frequency, so we get certain, we can see some sort of change in it. So let's look at here. What we got here? Let's make a new oscillator. Aha. That would be an error there. So I made a new oscillator, and here I can do mod dot sine wave open parentheses frequency. Let's make that. Let's go into oscillator 1 Hertz, say. So I know that's not much use, but then if we do frequency add this, so now it's going from whatever frequency is set to, I think that was 440 Hertz, plus or minus 1 Hertz, and then we can just times that by 40. Maybe that'll work. Maybe that will work. Also down here, what I'll do is I'll make it so we can change the frequency ourselves. So if I drag my mouse, then I can change the frequency. So frequency equals of map x between 0 and of get width. It's OF get width really, it's not of, is it? But that's fine. You're smart enough to know that. 0 and 0 and I don't know. Zero and 3000. That should be not too piercing. And I'm just going to turn it down as well because it was quite loud in the test. So if we go back to here, we can just make the whole thing quieter by dividing it all by 2. Okay, so we'll give that a run and see how that goes. I'm sure we'll probably bump into an error. Okay. So some typos here. A typo there. Typo there. That's not right. Let's try that again. Oh, hey, okay. That should be fine now. Alright, wicked. So we'll just wait for this to load up. So that's pretty cool. So I drag my mouse, the frequency gets bigger. Cool, so I hope you enjoyed it. There you go. Have fun with it, experiment. There's lots of better ways to draw this, but that's just a simple example to get you started. Take it easy. See you next time.